Okay, good morning everyone.
Good morning, sir.
So today we'll start with the new topic that is logarithms. So let's write down the definition first of all. If A is a positive real number and okay, real number other than 1 such that A raised to x is equal to m, then x is called logarithm of m to the base a, and we write x is equal to log to the base a of m. Very important notation. So what you are doing here, you are relating three numbers. So a, m, and x. What we have seen is say 2 raised to 4 is equal to 16. This we have seen. Okay. Like you have seen tan of pi by 4 is equal to 1. So tan goes on the other side and it becomes tan inverse. Right? Tan inverse of 1 is equal to pi by 4. The same thing if you have x plus 4 is equal to 13. So this plus 4 on the other side, it becomes 13 minus 4. So plus becomes minus on the other side. In the similar manner, when you have 2 raised to 4, so 4, this base 2 goes on the other side and it becomes log to the base 2 of 16. Okay. So this is the complete idea of logarithm. When you have base and you have some power and you have an answer, then the opposite side and this power are related by this relation. So if a raised to x is equal to m, then x is log to the base a. Okay, log to the base a of m. This is the most basic definition of log. Okay, now we'll just write some of the basic examples by which I can actually find out the log for many of the numbers. So examples: log to the base 10 of 10,000. Yes, anyone? Say call it say x, log to the base 10 of 10,000. Right? So I will call it say x. What happens to this log to the base 10 when it goes on the other side? 10,000 will be equal to, yes, anyone? Just
Sir, minus log to the base 10.
no. Try to relate this with this. If a raised to x is equal to m, then x is equal to log to the base a of m. Now my question is, if you have log to the base 10 of 10,000 equal to x, then 10,000 will be equal to
So 4.
but answer is exactly 4. So how do you get it? 10,000 is equal to,
So log 10 is equal to 1. And then find the value of log 10,000. So it's came 4. That's
and that is not the way I'm asking. I'm asking in this context. How can you relate this to? So this log to the base 10, when it goes on the other side, it will become 10 raised to x. So what power of 10 will give you 10,000? So 10 raised to 4 is actually equal to 10 into 10 into. So that will turn out to be 10,000. So that is what I am trying to explain. So log to the base 10, when it goes on the other side, it will take this x as the power of this base. So log to the base 10, on the other side 10 raised to x. Okay, so this is 4. Now if you have at least tried to understand this, then you can answer this. Look, if in the stational exam I will ask this question at least once. Just declare it right now. Log to the base 5 of 25 is equal to x. So 25 will be equal to, what will happen on the other side? 5.
5 raised to x.
So what
X
power of 5 will be 25?
5.
5
2. 5.
2 2.
What power of 5 will become 25?
2.
2.
So, so this will be equal to 2. So I can write it down here as 5 square is equal to 25. First, second, third. Log to the base root 2 of 32. So call it x. So log to the base root 2 is equal of 32 is equal to x. So 32 will be equal to root 2 raised to x, right? Now 32 is nothing but 2 raised to, how many times we have to multiply 2? 4 times, then it will become 16 into 2, you will get 32. So 2 raised to 5 is equal to 2 raised to root 2, I can write as x by 2, right? So this 2 and this 2 will get cancelled out. X is equal to 5 by, oh sorry, 5 into 2. So x is equal to 10. If you want, you can write this calculation down so that you can relate another examples. So in the definition itself, now looking at one simple example, the fourth one, log to the base a of 1. What will be the answer, anyone?
Sir, a raised to x.
So a raised to x, 1 is equal to a raised to x. When will you get a raised to x is 1? Say a is any number. When will this happen? I mean, for any number raised to x, for what power you will get answer as 1?
1.
Sir, 0.
0. So laws of indices says that any number raised to 0 is equal to 1. Okay. So by laws of indices, this log to the base a of 1 will be equal to 0. Look, your base plays a major role over here. Fifth, log to the base a of a. So you will get a is equal to a raised to x. When will this happen? For what value of x these two will become equal?
1.
1. So log to the base a of a is log to the base a of a is 1. Now log to the base a of 0. Yes, anyone? So what we will get? 0 is equal to a raised to x, right? And if a is not equal to 0, we consider this. In the definition itself, I forgot to write it down, but there is a condition that a should always be greater than 0 and not equal to 1. There is a condition with the definition of logarithm itself. So can you identify, say I'll take a is equal to 2. So 0 is equal to 2 raised to x. Can you identify x? At that power, answer will turn out to be 0. So is there a number that power of 2 will turn out to be 0? So, is it possible? Let me frame the question this way. Is it possible? So, can you have a power of x so that the answer will turn out to be 0? So, 2 raised to minus 1 is 0. That's what Kushi wants to say. 2 raised to minus 1 will be 1 by 2, not 0. Mihir? Where is Mihir? Mihir, is it possible?
Sorry, sir, I didn't get this.
You didn't get this. Aditi, is this possible?
Sir, I just joined right now. I don't know what is going on in the class.
Okay, the question is, okay, is there a power of 2 so that answer will become 0? 2 raised to x is equal to 0. Can you find the number x so that power of 2 will turn out to be 0?
No, sir.
No. Okay, so one more answer we have got. It's impossible. Okay. So for this, you will never have a solution. I mean, you take a power of 2 and it will always be non-zero. Of course, if you go on taking negative numbers, then it will become smaller and smaller, but it will never be equal to 0. So log to the base a of 0, log to the base a of 0 has no solution. Has no solution. Okay. So always remember these three properties. I mean, these are the basic properties of logarithm. Log of 1, whatever the base, log of 1 is always 0. Log to the base a of a is always 1. And log to the base a of 0 is not defined. I mean, you won't get a solution for it. For the late students, a raised to x is equal to m, then x can be written as log to the base a of m. So, log is the opposite of that power operation. When you give power, that base can be taken on the other side with log to the base a. So now, there are two types of logarithms which you have been doing in your classes. Maybe you were multiplying it by 2.303. You were sometimes it is simply ln, sometimes it is log. So these things we need to discuss. But before that, some important theorems which will be used a lot of times in different examples and in different places. First one, log to the base a of m into n is equal to log to the base a of m plus log to the base a of n. So what is important about log? So if there is a product and you have log, I can simply write it down as addition. One thing you should identify, I mean, doing addition and subtraction is very much easier for me than doing multiplication and division. The reason why we study log is log helps you to simplify lot of difficult expressions. Difficult calculations can be done very much easily using log. And this property plays a major role. If you see the left hand side, there you are multiplying, whereas on the right hand side there is division. Addition. So what log does is log says that instead of multiplying you add. Okay, that's what it does. So the first theorem is log to the base a of product of two numbers will actually be equal to log of first number plus log of second number. How do we prove it? I will give you the proof for one theorem. Others you can try on your own. Say log to the base a of m into n. I'll call it x. So m into n will be equal to
A raised to x.
a raised to x. So now I will call log to the base a of m is equal to y. Log to the base a of n is equal to z. So n will be equal to a raised to z. M is equal to a raised to y. Right? So I have these three values over here. So what I will do, I'll substitute this. So a raised to x, what I've got, a raised to x is equal to a raised to y into a raised to z, right? M into n, that's what m into n is. So m into n, this is what I'm doing here. So m into n is a raised to x, and m into n also can be written as a raised to y into a raised to z, right? So this is nothing but a raised to x is equal to a raised to y plus z, right? Which means that x is equal to y plus z. Let's put the value of x, y, and z. X is log to the base a of m into n. Y is log to the base a of m plus z is log to the base a of n. You have any difficulty over here? If I consider no. So in the similar manner, we can also prove this for division. So logarithm says that if there is a multiplication, you add. And logically, if there is a division, division, then what we should do is we should subtract. second one, log to the base a of m by n. This is equal to log to the base a of m minus log to the base a of n. So if you want a simple proof, put log to the base a of m by n is equal to x, a of m is y, a of n is z, and you simply do the thing. Third one, log to the base a of m raised to n. This is equal to n log to the base a of m. So what the third property says is, if there is a power, then I can take it outside. I mean, and multiply it simply. Okay. So taking a power is quite difficult than simply multiplying. So that is what log doing. Log is simplifying everything for you. Okay. So if I want to prove this, I'll take m raised to n is equal to a raised to x, right? And on the right hand side, what we have, log of a raised to m. So what we are going to have here is m is equal to a raised to y. Then you do m raised to n. Okay. So m raised to n, this thing will be equal to a raised to y raised to n, which is also equal to a raised to x. So if you simplify this, ny will become x. So you put the value of y, n into log to the base a of y is equal to log to the base a of m raised to n. Okay, log to the base a of m. Okay, so it is just the simple properties of indices that we are doing in the proof. The fourth one, change of base. So log to the base a of n is equal to log to the base e of n upon log to the base e of a. Can anyone tell me what is e? Anyone? What is e?
Sir, it is a power.
No.
E equals to 1.
E equals to 1. So e is
Sir,
an
constant.
e is an irrational number. So there were some irrational numbers that you have studied in your previous classes. One of them is e. It is an irrational number whose approximate value is 2.718 something. Okay, so wherever you see this e, so you must, I mean, consider it as an irrational number. What do we mean by irrational number? Is it cannot be written in the form of p by q. So rational numbers q, this you can write it down in p by q form. Okay, and irrational numbers cannot be written in the form of p by q, where p by q are co-prime. Co-prime means there is no common factor in them. So irrational number cannot be written in this form. Also, these irrational numbers जो decimal के बाद के points होते हैं, those are non-repeating, non-terminating. Okay, so that's why irrational numbers like e, also pi. Pi is also an irrational number whose approximate value is 3.14. Okay, remember this. Pi and e, this you will require everywhere. I mean, whatever branch you are studying, pi and e are very important. So e is an irrational number whose approximate value is 2.718. Whenever you are deriving any relation in thermodynamics or anywhere, so there you multiply by 2.303. Okay, it is because this e is there somewhere. We'll see later where it is and why you multiply by 2.303. But right now just understand, small e means irrational number whose approximate value is 2.718. So next, first one is natural log. Logarithms to the base e. To the base e are called natural log. And is denoted by ln. In mathematical terms, it is denoted by ln. And there is another type of log which is common log. Logarithms to the base 10 are called common log and is denoted by log. So when it is written complete log, it is log to the base 10. When it is written simply ln, it is natural log. The reason why it is called natural log, when you take integration, so you may or may not have heard about this 1 upon x dx. We'll see this in our syllabus. So when you take the integration, you get ln of x. Okay, and this ln of x, this is the natural log. Even in your 12th standard, you have done this in chemistry, thermodynamics. Okay, Even if you had physics, then you're doing this integration. You may or may not know about this a lot, but there was coming this log, and this was simply ln of x. So it comes naturally in the expression when you take integrations, and that's why it is called natural log. So if I want to convert log to the base e of x to log to the base 10 of x, we multiply by 2.303. Fine. Now comes the most important part. Why do we learn logarithm? So log to the base 10 of 254 if I am finding out. If this is equal to x. Now my question is, can you at least give some idea about x? I mean, what the number can be. It may be greater than 3, greater than 2, less than 2, greater than 5. Can you give some idea about it? Can you think about it? That's my question. Can you guess what that number can be? Before guessing, just tell me 254 will be equal to
10 raised to x.
10 raised to x. So x has to be equal to something, right? What that value can be. Can you identify two numbers between those this value of x will lie? Okay, tell me, can power of 10 become 254?
No, sir.
No. So what is the nearest power that you can get to that? So if I make 10 square, what this will be? 100.
100.
If I make 10 cube, then it will become 1000, right? 254 is between these two, 100 and 1000. So the value of x has to be 2 point something. Am I right? Are you convinced with this point? जैसे कि I need 2 raised to some power become 254, right? I want this. I need a power of x so that my answer will become 254. But what
Sir,
I
2 raised to 18.
yes,
2 raised to 18.
no, you just understand what I'm saying. So I need a power of 10 so that it will become 254. Okay, so I know that 10 raised to 2 is 100, 10 raised to 3 is 10 raised to 3 is 1000. So the value of x must lie between 2 and 3, right? So it will be 2 plus something. So this is something that I have to find out. So this 2, the integral part, it is called the characteristic. Look, if you haven't understood it, no problem at all. There is a rule by which you can always find out the characteristic. But if you understand it, that will be much better for you. Okay. So let's write down the definition. characteristic. The integral part of logarithm is called characteristic. The other one is Mantissa. The fractional part of logarithm is called Mantissa. So for an example here, log to the base 10 of 254. This is 2 plus a fraction something 0 point something you will get. This 2 is called the characteristic. And this fractional part is called the mantissa. Okay. Now, up to this, if you haven't understood what is characteristic and mantissa, then these rules are for you. So you can find logarithm of any number using these rules. Okay. So rule number 1. Characteristic of a logarithm to the base 10. 10 is a 1 less than 1 less than the number of digits. The number of digits in integral part and is positive. And is positive. For this rule is for numbers greater than 1. For number greater than 1. So immediately I will write down some examples. So what do I mean by integral part is the part which is before the decimal point, that is called the integral part of a number. So characteristic of log to the base 10 of say 259.68 is. So what is the integral part? 259. So this thing is before the decimal point. This is called the integral part. Right? How many digits are there? 3. What the rule says? 1 less than the number of digits. So characteristic is 3 minus 1 is 2. Right? Characteristic of log to the base 10 of 9.568 is, yes,
0.
so it is 0. Is 0. So the second rule will say when your number is less than 1. Okay. Characteristic of logarithm of a decimal fraction of a decimal fraction is 1 greater is 1 greater than number of zeros immediately after the decimal point. After the decimal point and is negative. Example, characteristic of log to the base 10 of 0.2 is. So what the statement says, characteristic of logarithm of decimal fraction is 1 greater than number of zeros immediately after the decimal point. How many zeros in this number are there after the decimal point? 0. So 1 greater, so that is 1 and is negative. So the characteristic of this will become minus 1. This is the first one. Second one, characteristic of log to the base 10 of 0.00124 is anyone?
Minus 3. Minus 3.
Okay, so there are two zeros immediately after the decimal point. So one greater than this, so that will be 3, and your characteristic is negative in this case, so that is minus 3. Exactly right. Okay, so when I want to find log of any number, log to the base 10 of x, say a, then that will be characteristic plus mantissa. Okay, this is how we find the log of any number. And when I want to find log of any number, characteristic we have understood. Now the question is about mantissa. So I have already conveyed that you must have your scientific calculator with you for today's lecture. So please open your log tables. Let's turn the rules to find mantissa. So that is rule number 3. To be found using log table made of 4 figure first 4 digits of any whole number are to be used. So we need to find, say, now log to the base 10 of, I want to find, say, 2364. What is the characteristic of this? Characteristic plus
One.
mantissa. Plus mantissa. What is the characteristic? Someone said it.
1.
How it is 1, Mansi? What is
Because
the
it is a positive digit, and whenever it is a positive digit before the decimal,
how many digits?
you
How many digits
there
are
are two
there?
digits.
2 digits before decimal point. 2, 3,
Before
6.
the decimal point.
There are 4 digits.
Oh, yes.
So what will be the characteristic there?
3, sir.
3. 1 less than the number of digits. So 3 plus. Now in your table, logarithm table, what we are going to see is 2, 3, 6, 4. Okay. Look at the row in your table where you find 23. So wherever you find 23, then you look at the sixth column. So what is the value? So you will see 2.3. Look, in the first row you will have to see 2.3. Then you will have to move along this in the column of 6, and there you will find the number 3729. If you have got it, please raise your hand. Do you see the same number 3729 in the log table?
Yes, sir.
So others don't have the logarithm table. Okay. So now what is our last digit? We have used 2, 3. Then I have used 2, 3, 6 I have used. Now I have to use 4. Now there will be small columns at the end, most right hand side. So there you will have to look at the 4. Whatever is the number corresponding to 4, you will have to add it to this number 3729. What is the number you see corresponding to 4?
7.
7.
7. So add 7 to this 3729. So 3729
36.
plus 7.
3736.
3736. 3736. So the mantissa
Sir,
for
can you
this is
explain again?
0.3736. Okay. Now we just add them, and that is our log value 3.3736. Okay. Clear? If you have any doubt, please ask.
Yes, sir.
Sir, can you explain again?
So who has a problem in this? Someone is saying, can you explain again?
Yes, sir, me and Anya.
So I want to find, say, log 10 of 2364. So log of any number is actually equal to characteristic plus mantissa. Okay. Now the way I have to define a characteristic is this. I will look at this number. It is greater than 1. So whenever it is greater than 1, you calculate the digits or find the digits before the decimal point. So there are 4 digits. So 4 minus 1 is 3. 3 becomes the characteristic. Now I want to look at the mantissa. For the mantissa, in this given number, you find in the table, first of all, check out the row for first two digits, 2, 3. Okay. So in the log table, you find out 2, 3. And then you go horizontally in the column of 6, because my third number here is, so the number I'm calculating is 2364. So I will break this number into 3 parts, 2, 3, 6 and 4. So first of all, look at the row for 2, 3. When you go to the column of 6, so there you will find in your log table, you will find out this number 3729. Okay. Once I find this 3729, look at your fourth digit in the number, which is 4. So at the most right hand side, you will see small columns. In that, I will find out 4. So the number corresponding to 4 in your table, as you can see, probably is 7. So what I have to do is I have to add this 7 to this number 3729, and whatever I have got 3736, this is my Mantissa. So I have to write it down as 0.3736. When you add this to 3.3736, this is the log of 2364. Okay. So this is how you find the log. And how is this useful now? Okay. Say example. Find under root 0.395 whole square 2.45 upon 8.034. If I want to find out, I'll call this number say x. So x is equal to under root 0.395 whole square 2.45 8.034. So what I will do is I'll take log on both the sides. So log x is equal to log of this term 0.395 square 2.45 divided by 8.034 bracket complete square. What is the property? Log m raised to n. So this will be 2 times log of this number 0.395 whole square 2.45 upon 8.034. Right? Now there is a division. So if there is a division, what the property says is you subtract log of the numerator 0.395 square into 2.45 minus log of 8.034. Correct? Now what else? Now here there is a multiplication of two numbers. So again the properties of log says that this product can be written as addition. Log of 0.395 square plus log of 2.45 minus log of 8.034. Okay. So again log a raised to b is there. So this will be 2 times log of 0.395 plus log of 2.45 minus log of 8.034. Clear up to this? Now I can find out the values. So let's do it quickly. So 2 times log of 0.395. What is the characteristic of this? There's a decimal number. How many numbers of 0 are there after the decimal point? None.
Sir, it will be -1.
-1 is the characteristic.
What happened? -1, right? So this negative, I'll write it down as 1 bar for an example. 1 bar dot. Now 39, the row 39 and column 5. What is the number? 39 column 5. What is the number?
5966.
Are you able to find out?
minus 0.403.
In your log table?
Yes, sir. Log of 0.395.
Yes, Om, what is the number?
5966.
66 or 77?
66.
Okay, 66. Plus log of 2.45. There's one digit after the decimal point, I mean before the decimal point, number is greater than 1. So 1 minus 1, this will be 0 point. The row 24 and column 5.
3892.
3892 minus. There's one digit up before the decimal point. So I will have to subtract 1, 1 minus 1, 0 point. Look at the row 80, third column. 80, the column of 3, which is
9047.
9047.
and look at the 4 entry
9049.
and there is 2 for the entry 4, right? I would have to add 2 to this 9047, so that will be 9049. Okay, so we can add, subtract, do whatever I want with this. So this will be 1 bar, so minus 1 into 2 minus 2. Okay, so I will get some number here. Say I won't do the calculations right now. I'll get some number over there. Say 0.39 this minus this, and say if I got 2.3848. Okay, so log of x. Look, I'm assuming this number I have got 2.2848. So what I have to do is, what is my task to find out x? So x will be anti-log of 2.2848. Okay, so I need to find out anti-log now. So how do I find out anti-log? So if you have logarithm table, there you will also see anti-logarithm table. So in the next lecture, what we will see is how to find the anti-logarithms. Right now, what we have seen, how to find the logs. The next lecture, whenever it happens, so at that time we'll see how to find anti-logs. Before that, we'll solve some examples based on these properties that we have studied. Example, if x is equal to log to the base 2a of a, y is equal to log to the base 3a of 2a, and z is equal to log to the base 4a of 3a. Then prove that x, y, z plus 1 is equal to 2y, z. So consider the LHS for an x, y, z is equal to log to the base 2a of a into log to the base 3a of 2a into log to the base 4a of 3. Can you find something from here? You have to speak something. I mean, you cannot just sit quiet. Even for characteristic and Mantissa, there is a lot of silence. Yes, tell me. So how can I write down? I'll give you some hints. So log of a upon log of 2a. So here you have base e. Y I can write as log to the base e of 2a upon log to the base e of 3a. This is change of base formula, and z is equal to log to the base e of 3a upon log to the base e of 4a. Now can you do something? Okay, if this sounds difficult, I'll change my question to this. Show that 1 upon log to the base 6 of 24 plus 1 upon log to the base 12 of 24 plus 1 upon log to the base 8 of 24 is equal to 2. No one? You have to just consider the LHS and do the calculation. That's it. There's nothing difficult in this. So what is LHS? Log 6 upon log 24, both base e by the change of base formula. You'll have log 12 upon log 24 plus log 8 upon log 24. Now all the base denominators are same, so I can add the numerator. Log to the base e of 6 plus log to the base e of 12 plus log to the base e of 8 upon log to the base e of 24. So we know that since there is this addition, instead of adding log to the base e, I can multiply 6 into 12 into 8. upon log to the base e of 24. So 6 into 12 into 8, which is log to the base e of 576 upon log to the base e of 24. So 24 into 24 is 576. So log of 24 square upon log of 24. Again use the property of log. Log 24 square is 2 log 24 upon log of 24. This 2 will get cancelled out and the answer is 2. You just have to use the properties in a proper manner. Fine. Let's come back to this. Now can you at least pick something in this?
So do we have to just put the values of x, y, z in that equation?
And what you will do? By putting the values, you cannot simplify further. How will you multiply? So we will have to consider x plus y, log of a plus b plus c. So log of 2a, log to the base 2a plus log to the base 3a, 2a plus log to the base 4a, 3a, and by consideration we will have to solve. But anyway, we won't be doing it today. I'll do it in next lecture now. Everything else will be done in the next lecture. So Ananya Mandal is here.
Yes, sir.
It came early today.
What, sir?
When did you join?
Sir, I was a bit late.
Okay. See you all in the next lecture.
Sir, what is